Hi everyone, today we are going to learn how to graph rational functions that are a little bit different than what we've already done before. This time around we're actually going to be working with quadratics and factoring in order for us to come up with key pieces of information to help us to graph our functions. Before we get started though, I would like you to please go ahead and factor x to the fifth minus x cubed plus x squared minus 1. It has 4 terms in it, so I want you to start off by using factoring by grouping, and then keep your eyes peeled for opportunities to use dots, difference of 2 squares, or the skills that we've learned from sum or difference of cubes. When you have an answer, go ahead and restart the video and we'll see how well you did. Okay, so like I said before, this is 4 terms, so that means that we're going to put parentheses around the first 2 terms and the last 2 terms. The first 2 terms, we need to come up with the greatest common factor, and we need to factor it out. X to the fifth and x to the third both have at least 3 x's, so I'm going to factor out an x cubed, with my leftovers being an x squared minus 1, plus x squared and 1 do not have anything in common, but what they do have in common is what every pair of numbers have in common, and that is the number 1. So I'm going to automatically factor out a number 1, and my leftovers is an x squared minus 1. You know you factored correctly when you have both of your parentheses being the same. So now I'm going to write a set of parentheses using my outsiders, which is an x cubed plus 1, and my insiders, which is an x squared minus 1. Now my first parentheses, this is a sum of cubes. X cubed is a perfect cube, 1 is a perfect cube, so it's a sum of cubes. So I'm going to factor that by breaking it down into a binomial times a trinomial. I'm going to take the cube root of the first term, and that's an x. My sign in the middle is a plus, and the cube root of 1 is 1. Now I'm going to use square, opposite, product, square. X squared, opposite of a plus is minus, 1 times x is x, and 1 squared is a positive 1. The second parentheses, x squared minus 1, is a dot, a difference of 2 squares, and we can break that down into 2 parentheses. So I have an x plus 1 and an x minus 1. I take the square root of the first term, that's going to be an x. In order to get a minus, you have to have a plus and a minus, and the square root of 1 is 1. To clean this up a little bit, since we have 2 parentheses that are identical, I can rewrite this as x plus 1 squared. Then I can write x minus 1. And then my trinomial, which is x squared minus x plus 1. And that is your answer. So hopefully you did pretty well at factoring. Will I give you something this intense on your test? No, but what I will do is I will give you a problem where you'll have to do factoring by grouping. I might give you a problem where you'll have to use stops, and I might give you a problem where you have to use dots, or I might give you a problem where one of those will be embedded in the problem. So you always need to keep your eyes peeled for opportunities to break problems down even further. All right, here we go with our lesson. Our learning target for today is to be able to say, I can graph rational functions when the degree of the numerator is less than the degree of the denominator. And I want you to be able to say, I can graph rational functions when the degree of the numerator and denominator are both 2. So we might have a quadratic over a quadratic. So the degree is going to both be 2. So that means the shape of our graph is going to be a little bit different, but we're going to be using some of the same skills and the same strategies that we learned in the last video as well. So for this lesson, I would recommend that you use a pencil. I would also recommend that you use a highlighter. And I would also recommend that you have out your gold sheet, something to refer to throughout the entire process. So I have all of these pieces of information out, and here we go. So whenever you graph rational functions, we already have talked about the fact that a rational function is where you have a polynomial over a polynomial. We've worked with linears and constants over a linear over a linear and a constant over a linear before, but now we're going to be working with potentially quadratics and constants, etc. So that's what we know before. That's what we've done before. So now what we want to do is we want to kind of talk about how to identify those x-intercepts and the key pieces of information. I've actually already talked to you guys about in the last video how to identify your x-intercepts. Now your x-intercepts of the graph are the real zeros of the graph. How do you come up with your zeros? Well, that happens whenever you let y equal 0. And the only way for a fraction to equal 0 is if the numerator is equal to 0. So if you have 0 over a number, that is equal to 0. So if we wanted to identify what our x-intercepts are, we let y equal 0. And the only way for that to happen is if we let our numerator equal 0. So to find our x-intercepts, we're going to let our numerator equal 0. So whenever you let your numerator equal 0, you'll end up with your x-intercepts. And so they are the real zeros of p of x. So that is your numerator polynomial. The graph has a vertical asymptote. And I talked about this in the last video as well. In order for you to find your vertical asymptotes, that's going to take place where we have restrictions on the domain. The domain restrictions are related to one another. And we know that there's going to be restrictions on the domain if we have a 0 in the denominator. So if you have a number over 0, we end up with a no way situation, which means that we'll have a restriction on the domain and we'll end up with asymptotes. So how do you identify your vertical asymptotes? Well, you let the denominator equal 0. So our denominator, according to our statement, is q of x. So we're going to let q of x equal 0. So this is our numerator, p of x is our numerator, and q of x is our denominator, just based on our little piece of information that's already given to us. So for step 3, the graph of f has at most one horizontal asymptote, which is determined by the degrees. And the degrees we're going to call m and n of p of x and q of x respectively. So that means that when I refer to p of x's degree, I'm going to refer to it as m, and q of x's degree is going to be n. And this information is information that we've already talked about on our yellow sheet. So I'm just recapping step 4, how to find the horizontal asymptotes. We've talked about if the degree of the numerator is less than the degree of the denominator, then our horizontal asymptote is automatically y equals 0. So if you have m is less than n, then the line y equals 0 is your horizontal asymptote. So if the degree of the numerator is less than the degree of the denominator, your horizontal asymptote is 0. According to the yellow sheet, if your degrees are equivalent to one another, then that means that your horizontal asymptote will follow the equation of the leading coefficient of the numerator divided by the leading coefficient of the denominator. And that coefficient is the number that's in front of your variable with the highest degree. So according to our little polynomials that we have up here, I have my leading term being a sub m times x to the nth power and b sub n times x to the nth power. So our leading coefficients are a to the nth and b, or a sub n and b sub n. So our horizontal asymptote is going to be a sub m divided by b sub n, and that represents the leading coefficient of the numerator divided by the leading coefficient of the denominator. And that only happens if our degrees are the same. Our last thing is if the degree of the numerator is bigger than the degree of the denominator, then that means that the graph has a slant horizontal asymptote, and that's something that you'll learn in pre-calc. If you don't go to pre-calc and you go to Algebra 3 with Trig, you'll learn it in Algebra 3 with Trig as well. So that's a pre-calc concept that we're not going to focus on in this class. So let's go ahead and hop right into graphing these functions. So the thing that I want you guys to know about these functions, that whenever you have a quadratic somewhere in your problem, like in this case we have a quadratic in our denominator, and all of the other problems that we're going to be working with will have a quadratic. If you see a quadratic, then that means that your domain and range are going to be a little bit different than what we've identified before. I'm going to call it even tricky. So the domain and range are tricky to identify. No big deal though. How do you handle the trickiness of the domain and range? Well, you identify it last. You need to look at your graph and actually graph all of your information first and then determine your domain and range. So what I'm going to say is, in order for you to identify your domain and range, look at your final graph. And then decide what your domain and range are actually going to be, because it's going to be different than what we had last time. All right, so the first thing we're going to do is we're going to identify our x-intercept. And we just discussed that in order for you to identify your x-intercept, we're going to let our numerator equal 0. And that's because whenever we identify our x-intercepts, we're letting y equal 0. So whenever you let y equal 0, we're essentially letting the numerator equal 0. So my numerator in this case is 3, and 3 is supposed to equal 0. But unfortunately, they are different numbers, so therefore we have no x-intercept. My vertical asymptote, that happens when you let the denominator equal 0. So I'm going to let x squared plus 2 equal 0, and I'm going to solve for x. So I'm going to write x squared plus 2. I'm going to write down, I'm going to let the denominator equal 0. I have x squared plus 2 equals 0. I'm going to subtract 2 on both sides, and I end up with x squared is equal to negative 2. In order to get rid of the square root, I'm going to take the square root of both sides, and I end up with x is equal to plus or minus I square roots of 2. So cool, we ended up with 2 solutions, but I said that your vertical asymptote needs to be a real 0 of the denominator, and both of these are imaginary. So what that means is that this time there was no vertical asymptote. So there's nothing for us to graph so far. So now I said wait on your domain, actually look at the graph before you make that decision. And now we're going to look at our y-intercept. Our y-intercept happens when you let x equal 0. So that's exactly what we're going to do. I'm going to write y is equal to 3 divided by 0 squared plus 2. 0 plus 2 is 2, so we end up with 3 over 2. So y equals 3 halves, or you can write it as 1.5, which is a little bit easier to graph. So I have my y-intercept at 0, 1.5, and if you want to make sure that you graph that so you don't forget to graph your y-intercept, go ahead and plot it. That's not a big deal. Next, we have our horizontal asymptote. So we need to look at the degree of the numerator and how it matches with the degree of the denominator. Whenever you see just a number, that means that the degree is 0. So we have the degree of the numerator is 0, and the degree of the denominator is 2, and 0 is certainly less than 2. So what that means is that since our degree of the numerator is less than the degree of the denominator, that means that our horizontal asymptote will be located at y equals 0. So I'm going to go to where y equals 0 is, and I'm going to draw a dashed line with arrows at each end, and then I'm going to take out my highlighter and highlight over it so that it is obvious, bold, and clear. Next, I'm going to wait on my range, and I'm going to wait for me to actually come up with my graph before I make that decision. Now before, whenever we made a table, it was based on their vertical asymptotes. And since we don't have any vertical asymptotes, that means we just need to come up with a basic table where we have negative values all the way to positive values. So I'm going to choose negative 2, negative 2, negative 1, 0, 1, and 2. And for time purposes, I'm going to plug all of these numbers in. And at -2, we have 1/2. At -1, we have 1. 0, we already know that's going to be 1.5. 1, we have 1. And 2, we have 1/2. So I'm going to plot these ordered pairs. And I'm going to plot -2, 1/2. So that's -1, -2, 1/2. -1, 1. 0, 1.5. We already have graphed. 1, 1, and 2, 1.5. Now, we know that this graph is not allowed to cross our asymptote. So what this shape is going to look like is a bell. So I'm going to have my graph approach the asymptote, and I'm going to make a curved look. So it might appear like it should be a V, but it really in reality needs to be a bell shape. So try to make it a little curvy and have it approach the asymptote. Now we're going to identify our domain and range. Notice that there's no gaps. There's nothing that's preventing our graph from going to the left or going to the right. There's no vertical asymptotes. And when you notice that there is no vertical asymptote, that means that your domain is not restricted. So our domain is going to be all real numbers. X can be any number. We've got a solid line pointing to the left and pointing to the right. Our range is a little different. For our range, we notice that our graph is not below our asymptote. Also notice that there's not an arrow pointing up. So it reaches a maximum value. And that maximum value is located at our y-intercept, which is at 0, 1.5. So we reach a minimum value. It's going to approach our asymptote, which our asymptote is 0. So our range is going to be 0 is less than y, which is less than or equal to 1.5. The reason why we have less than is because it never will cross our asymptote at 0. And it reaches a maximum at 1.5. And that it actually touches 1.5 at an actual point, so that's why it's included. So that is our first graph. So what I want you to do is I want you to try example number 2, which is very similar in structure, on the next page. On your own, I want you to pause the video to do this. And when you have an answer, please restart the video and we'll see how well you did. All right, so the first thing we need to do for this problem is we need to identify our x-intercept. And that happens whenever you let y equal 0, or in other words, you let the numerator equal 0. So when I let the numerator equal 0, we have 12 equals 0, which is not true. So that means that there is no x-intercept. For a vertical asymptote, I have x squared plus 4 is equal to 0. I'm going to subtract 4 on both sides, and I end up with x squared is equal to -4. Now, if you know automatically at this step that this is not going to produce anything real, then you can automatically go straight to none, that this is not going to produce any sort of real vertical asymptote. So we have none. I'm going to skip my domain and my range, and I'm going to go on to y-intercept. So my y-intercept happens when you let x equal 0. So I have y is equal to 12 divided by 0 squared plus 4. 0 squared plus 4 is 4, so this is 12 over 4, which is 3. So at the ordered pair 0, 3, that is my y-intercept. And I'm going to make sure that I plot it so I don't forget it. Next, my horizontal asymptote is based on the degrees, and the degree of the numerator is 0 because it's a constant, and the degree of the denominator is 2 because it's quadratic, and 0 is certainly less than 2, so that means that my horizontal asymptote is automatically at y equals 0. So I'm going to graph y equals 0. Next, I'm going to come up with a table of values, and in my table of values, since I have no restriction based on the vertical asymptotes, I'm just going to choose values of x starting at -2 and going to +2. So I'm going to go -2, -1, 0, 1, and 2. For time purposes, I've already come up with these values for you, but you would plug them into your scientific calculator to come up with them. And we end up with 1.5. From -1, we have 2.4. Just round, whenever you do these problems, round to the nearest tenth. That's easier to graph if you round it to the nearest tenth. We're going to be approximating anyways, so it's not that big of a deal. if you just round like that. 0, 3, we already knew that. Then we have 2.4 and 1.5. So now I'm going to plot all of these points on my grid, and I have negative 2, 1, 2, 1.5. Then I have negative 1, 2.4. 0, 3 is already graphed, and then I have 1, 2.4, and 2, 1.5. Remember that this shape is a bell shape, so you want to make sure that your graph looks curvy and not like a V in the center. And now we're ready to identify our domain and range. For our domain, there is no restriction, there's no random lines, no holes in it, so our domain is going to be all real numbers. And our range, well, since we don't have anything going below our asymptote, that means that our range will start at 0. So 0 is less than y because our y values will never cross our asymptote, and it reaches our maximum value. Now, that maximum value is typically going to be located at your y-intercept. Our y-intercept is 3, so I have 0 is less than y, which is less than or equal to 3. It typically will be that, so just keep that in mind. Now, if we have a reflection across the x-axis where our bell shape is below, then that means that our inequality symbols will reverse, and that might be something that you'll see in your homework. Okay, let's go ahead and transition to something a little bit different. This time around, we're going to have degrees that are the same, and both of these degrees are going to be quadratic. So in examples 3 and in example 4, we have a quadratic over a quadratic. So the first thing we want to do is, just like we've done in all of the other problems that we've had, is we need to identify our x-intercepts. And just like before, for our x-intercepts, we're going to let our numerator equal 0. So my numerator is x squared minus 9, and I'm going to set it equal to 0. Now, x squared minus 9, that's a dot. That's a difference of 2 squares. So we can factor it into x plus 3 times x minus 3 is equal to 0. Another approach is to simply add 9 to both sides and take the square root of it. The thing is, though, is that whenever you work with square roots, you have to remember that you have a plus or minus as a part of your answer. And in this case, we have 2 x-intercepts. X equals negative 3 and x equals positive 3. So our 2 x-intercepts are located at negative 3, 0 and positive 3, 0. And if you want to make sure that you graph those right away so that you don't forget them and you don't lose points, I would recommend that you do so. So this is going by 1, so I'm going to go 1, 2, 3, 0, and here is negative 3, 0 and positive 3, 0. Next, we have to graph or identify our vertical asymptotes, and that happens when you let the denominator equal 0. So I'm going to let x squared minus 4 equal 0. This is also a dot, a difference of 2 squares. So therefore, I'm going to break it apart into 2 parentheses. X plus 2 times x minus 2 is equal to 0. So I have 2 vertical asymptotes at x equals 2 and at x equals negative 2 and x equals positive 2. So I'm going to draw both of those vertical asymptotes at this time. So I'm going to go to where x is equal to negative 2, and I'm going to draw a vertical line going through x equals negative 2, and a vertical line going through where x is equal to positive 2. I'm going to wait on my domain just like we did before, and now I'm going to go into my y-intercept. My y-intercept happens whenever you let x equal 0. So I'm going to let x equal 0, and I end up with y is equal to 0 squared minus 9 divided by 0 squared minus 4. So this is negative 9 over negative 4, which is 9/4. So we can graph or plot 0, 9/4. 0, 9/4, 9/4, 4 can go into 9 2 whole times with 1 left over, so that's about 2 1/4. So we can graph that at 0 and 2.25 if that is helpful for you to write that down. And I'm going to plot that so I don't forget it. So 0, 1, 2.25. So it's going to be just above the 2. My horizontal asymptote is based on the degree of the numerator and the denominator. And in both cases, the degree of the numerator is equal to the degree of the denominator. 2 equals 2. So that means that our horizontal asymptote will not be 0. This time around, it's based on the leading coefficient of the numerator and the leading coefficient of the denominator. Remember that if your degrees are equal to each other, you're going to divide the leading coefficient of the numerator divided by the leading coefficient of the denominator. And since both leading coefficients are 1, we know that 1 over 1 is 1. So that is going to be my horizontal asymptote at 1. So at y equals 1, I'm going to draw a horizontal line going straight across. Next, before I identify my domain and range, I'm going to come up with a table of values. Your table of values are still going to be based on our vertical asymptotes, and in this case we have 2 vertical asymptotes. So I'm going to start with the smaller one, which is -3, and I'm going to pick 2 values smaller than -3, which are -5 and -4. Then I have -3, then I'm going to put a little squiggle line, and then I'm going to choose -2, -1, 0, 1, and then I have 2. So I'm choosing all of the numbers that are in between my vertical asymptotes. And then I have 3, which will have a squiggle line, and then I'm going to choose 4 and 5. So we choose all of the numbers that are in between 3 and -3. Now, for time purposes, I already have all of these values ready to go for you. So -5. I'm sorry. I think I just screwed this up. We're supposed to choose from our vertical asymptotes. My vertical asymptotes are -2, not -3. Jeez Louise. All right, so this is what I'm going to do. I'm going to erase off my -5s, and I'm going to put my -3 back in and put my squiggles in at 2 and -2. These are my vertical asymptotes at x equals ±2. All right, so now we're going to cross that off and cross that off. And at -4, we have 0.6. And at -3, we already know that that is 0 because -3, 0 is our x-intercept. -2 is my vertical asymptote. -1, we have 2.7. At 0, we have 2.25. For 1, we have 2.7. For 3, we have 0 because that's our x-intercept, and for 4 we have 0.6. So those are the values that we're going to use. And now I'm going to plot all of the points that I have not already plotted. So I'm going to plot -4.6. So this is -1, 2, 3, -4.6. It's a little bit up here. And on this side of the branch, I'm going to draw like a curve that's going around both of my asymptotes. In the middle, this is where it gets fun. I'm going to plot -1, 2.7. So this is 1, 2.7. So it's going to be about up here. And I already have my 0, 2.25, and then now I have 1, 2.7, which is about right up here. And our graph is going to be approaching our asymptotes, coming down to a minimum, and then going right back up. So we have this random quadratic that's in the dead center of our graph. And now I already have 3, 0 already plotted, and here's 4.6. And I'm going to draw another little branch on the side, another little curve. And that is our graph, which is totally weird and totally cool all at the same exact time. So let's go ahead and analyze what our domain is. So our domain has restrictions because it's based on our vertical asymptotes. So my vertical asymptote this time around is an x equals -2 and an x equals +2. And notice that x can be any number except those 2 spots. So our domain is going to be all real numbers except x cannot equal ± 2. So that is our domain. It's based, once again, on our vertical asymptotes. Our range depends on which part you're talking about. There are 2 portions. You're either part of a branch or you're part of the parabola. And both parts have their own range. So we're going to put an or in between our range values. So if you're part of a branch, the branches are below the asymptote. So it's going to be all values of y less than 1. Or you're part of the parabola, and the parabola comes down to a minimum, and that minimum value is located at 2.25, and then it's increasing. So it's either part of a branch, which is y is less than 1, or it's y is greater than or equal to 2.25. And that's your range. So your range will have two parts, and it'll be separated by the word or. If you would like to try example number 4 on your own, I recommend that you do so just to make sure that you understand what I just showed you here. If you want to sit tight and have me show you what to do, that's not a problem as well. Please pause the video though and try it on your own, and then we'll see how well you did once you restart the video. All right, here we go. Number 1. We need to identify our x-intercept. So my x-intercept, that happens whenever you let the numerator equal 0. So I'm going to let 0 equals 3x squared. Let's make sure you guys can actually read this. So now I'm going to divide both sides by 3. We end up with 0 is equal to x squared, and you take the square root of both sides, and we find that x is equal to 0. So 0, 0 is our x-intercept. So I'm going to plot 0, 0 because that is for sure a point on my graph. Next, I need to identify my vertical asymptote, and that happens whenever you let whenever you let the denominator equal 0. So I have x squared minus 16 equals 0, which is another dot. So this is a difference of 2 squares. So I'm going to have an x plus 4 times an x minus 4 equals 0. So x equals negative 4 or x equals positive 4 are my vertical asymptotes. So that's exactly what I'm going to graph. Now notice that my scale is going by 2, so please be careful. Both the x and y axes are going by 2s. So we're going to count 2, 4 in order for us to go to the left and right in order to plot our vertical asymptotes located at x equals negative 4 and x equals positive 4. So those are my vertical asymptotes. The next thing I need to do is identify my y-intercept. And my y-intercept happens whenever you let x equal 0. So I'm going to have y is equal to 3 times 0 squared divided by 0 squared minus 16. So this is 0 over negative 16, which is 0. So my y-intercept is at 0, 0. Unfortunately for us, we've already plotted it. Next, we need to identify our horizontal asymptote, and that happens whenever you, we analyze our degree of the numerator and the denominator before we determine what kind of number that is. And the degree, both degrees are the same, 2 equals 2. So therefore, our horizontal asymptote will be the leading coefficient of the numerator, which is 3, divided by the leading coefficient of the denominator, which is 1. So our horizontal asymptote is located at 3. So since we're going by 2s, I'm going to go 2, and then in the middle is where 3 is going to be located. Next, I need to come up with a table of values. Now, this table of values is going to be a little bit bigger than what we've done before. So I'm just putting that out there. So it's going to be based on our vertical asymptotes, and our vertical asymptotes are negative 4 and positive 4. So I'm just going to choose 2 values in between. So I'm going to choose negative 6, negative 5, 4 is an asymptote, and then I'm going to choose 3, 2, 1, 0, 1, 2, 3, 4 is an asymptote, 5, and 6. So I'm choosing all of the numbers in between just to make sure that I have a very accurate graph. And for time purposes, I've already have this table already filled out for you. So I have negative 6, 5.4, negative 5, 8.3. For 3, I have negative 3.8. For 2, I have negative 1. For 1, I have negative 0.2. For 0, we already have 0. For 1, it's negative 0.2. For 2, it's at negative 1. 3 is at negative 3.8. 4 is an asymptote. 5 is going to be located at 8.3, and 6 is located at 5.4. All right, here we go. We're going to plot these points. So I'm going to plot negative 6 246, negative 5.4, 246, so 5.4 is about right here, and negative 5 is in the middle, so it's going to be located in the middle right here, so it's going to be located at 246.8, just slightly above at 8.3. And here's my first branch. In the middle, we have a parabola, and we have negative 2, negative 3, 3.8, 2, 4, so 3.8 is about right here. Negative 2, negative 1, so it's going to be in the middle. 0, 0, 1, negative 0.2, and 2, negative 1. So 1 is going to be 0.2, so it's going to be right here. And then we have negative 3, 3.8, so it's going to be right here. I'm going to have this parabolic shape where I'm going to have both sides approaching each asymptote. And then now I have 5, 8.3, so that's 2, 4, 5, 2, 4, 6, 8, 8.3 is just right here. And 6, 5.4, so that's going to be 6, 2, 4, 6, 5.4 is about right here. And there's my other branch. So now, when it comes to your domain, it's based on your vertical asymptotes once again, so that's something very familiar to us. So all of our x values are touched except for where our vertical asymptotes are. So that means our domain is going to be all real numbers except x cannot equal plus or minus 4. My range, it just depends on if you're part of the branch or if you're part of the parabola. So we're going to have two parts, branches and parabolas. So if you're part of the branch is located above the horizontal asymptote. Our horizontal asymptote is located at 3, so y needs to be greater than 3. Or you're part of the parabola, and our parabola reaches a local maximum, and that maximum value is located at 0. So y needs to be less than or equal to 0 because we actually touch it. All right, that is the end of today's lesson. If you have any questions over anything, please feel free to email me. Otherwise, I hope you have a wonderful day.